Hi, now in this video, we are going to do some problem solving on these questions of chemical change. So now let us start with question number 7 and read it first. Now question number 7, it reads as follows. It says to us, methane is used as an alternative fuel. The combustion of methane releases carbon dioxide and water. The balanced equation for this reaction is as follows. So now what we see here on the screen is we have a chemical reaction. Now this chemical reaction is a reaction between methane and oxygen to produce carbon dioxide and water. And we know that this type of reaction, it is simply called the combustion reaction. But now do not forget, in this question, we are going to talk about the chemical change. So now, again, what we see here on the board is we have the energy in kilojoule per mole. Okay, we have the energy in kilojoule per mole, which is equivalent to 891. So now this energy, it is written in a form of a product in this reaction. It is not the reactant, it is written in a form of a product in this reaction. Now, we are also told that the activation energy for this reaction is equivalent to 172 kilojoule per mole. Now, when we talk about the activation energy, what are we actually talking about? We are talking about the minimum energy that is required for a chemical reaction to take place. So now, in order for us to answer these questions, let's just make sure that we are familiar with all the concepts that are aligned to this. Now, 7.1, it says to us, is the reaction endothermic or exothermic? Give a reason for the answer. So, in order for us to see that whether this reaction it is endo or exo, we need to judge by the energy which is provided to us. So the energy that's going to help us to judge that it is this energy over here, which is represented as your product. Now, each and every time, this is what I want you to know, okay? We are also going to give a reason why do we choose this endo or exo. So now this is what I want you to know. Each and every time when your reaction, say for an example, A plus B, they react together to form a product which is called C. Now let's say our energy in this case, it is treated in a form of a product. We know here we have the reactant side and then there we have the product side. So now in this case, we always say this type of reaction, it is exothermic reaction. But now, why do we say that? Because our energy, it is given off out of the product side. We are not using the energy in this reaction. Instead, or rather, we obviously use energy, but in this case, instead or rather, because the energy, it is written on your product side. So that means we are giving off the energy. But now, let's say, for an example, your reaction, it is written in this way. A plus B plus our energy, okay, remember this is energy, will give a product which is C, maybe, and D. Now, this type of reaction, because we are not giving off energy, so we are using up energy on the reactant side. This type of reaction, we're going to call it an endothermic reaction, meaning the forward reaction, it is endothermic reaction. Here, the forward reaction, it is exothermic reaction because we are giving off the energy. Okay? I hope that was clear. Remember, some type of reactions can be reversible. So if you are provided with equation like this, whereby it is reversible, when they say to you, is the forward reaction exothermic or endothermic? You're going to say the forward reaction, it is exothermic because you are giving off. But in the very same reaction, when they say is the reverse reaction endo or exo, you are simply going to say it is endothermic because we are moving from the product side to the reactant sides, meaning from the product sides, we are using the energy with C to provide or to yield into A and B if the reaction is reversible. I just want you to pay attention onto that. So now, is this reaction which is provided over here endothermic or exothermic? This question is very simple. After understanding this, our energy is on the product side, meaning it's going to be exothermic reaction. But give a reason for the answer. Why are we saying this is the exothermic reaction? Because it's simple, guys. What did I say when I was explaining there? I said it's because energy is given off, okay? Because energy is given out or off. It's because energy, it is given out of the system, out of the reaction as a form of product. It's living, okay? We are releasing heat. This is how we answer this question, which is 7.1. And then now 7.2, it says to us, explain why all chemical reactions need activation energy. Why all chemical reactions need activation energy. I say to you, the activation energy for this reaction, it is 172 kilojoules per mole. And then I have already defined what is an activation energy. I say to you, look, for something to be activated, we need energy. So what is that something that we are talking about? It is this chemical reaction. So for this combustion reaction to take place, we need something that will activate these molecules to interact with one another. Methane, in order for it to interact with oxygen gas, we need an activation. So that activation, it is called an activation energy. So this activation energy will cause methane gas and oxygen gas to interact with one another. But how? The activation energy will break the what? Will break this thing. The activation energy will break the bonds between the atoms of methane, will also break the bonds between the oxygen gas. After this bonds break up, and after these bonds of oxygen to oxygen break up, therefore carbon will most definitely interact with oxygen, right? And oxygen will most definitely interact with hydrogen, and therefore we're going to produce these two types of products that you see over here, which is carbon dioxide. Where does in carbon dioxide, where does carbon and oxygen comes from? Carbon comes from methane. Oxygen, this oxygen comes from the oxygen gas. So that means what made these bonds to break off? It is what we call the activation energy. So now the question here, it says to us, explain why all chemical reactions need activation energy. The reactions, every reaction that you can think of, it needs that. Why? So that the activation energy can break the bonds between the interacting reactants. That's simple as that. So in order for us to answer question number 7.2, why do we need, explain, we are explaining now why all chemical reactions need that. Because it is the energy that is required, okay? Energy needed or required, needed to break the bonds between what? The bonds between the interacting molecules. Okay, so when I say interacting molecules, or you can say the bonds between the reactants, I'm referring to the reactants because the reactants are the ones that are going to interact. But the thing is, for you to be safe, and so I'm saying interacting molecules, like I said, some type of reactions can be reversible, so you can't always say the energy needed to break the, you know. So but in this case, for you to make sense, energy needed to break the bonds between interacting molecules, okay, so that these interacting molecules can freely interact with one another after the bonds has been broken off. So that's how we answer this question, which is 7.2. Now we jump to 7.3. So now 7.3, it says to us, why is this reaction not considered to be environmental friendly? Look, The combustion reactions are not environmental friendly, simply because we all know that carbon dioxide, it is one of the greenhouse gases. Okay, we know that there are unwanted gases in the atmosphere which actually breaks the ozone layer. And when the ozone layer breaks off, what is going to happen with the whole planet? We're going to be, it's going to lead into a global warming. So now the combustion reaction, methane with oxygen, they produce carbon dioxide. We do not care about H2O because we know that this is friendly, but carbon dioxide, it is not friendly. Carbon dioxide, it is not our friend because it will do what? It is one of the gases of greenhouse effect. So why is the reaction not considered to be environmental friendly? Because of what? Because of carbon dioxide. Okay, so now how are we going to answer this one? Because the reaction produces what? It produces carbon dioxide, which is most definitely considered to be one of the greenhouse gases that leads to global warming. So remember, we don't want this gas at all. We know that the greenhouse gases, they most definitely lead to global warming. I mean, like the planet Earth will experience high temperatures, will be very hot because there is no ozone that protects us from the radiations from the sun. Okay, so that means the earth will heat up due to these gases that are not friendly in the atmosphere to our atmosphere. That's how we answer these questions. Now let us do this following question. Now, it says a barium hydroxide solution, which is given by this chemical formula, reacts with a nitric acid solution according to the following balanced equation. Here is your barium hydroxide reacting with your nitric acid solution to give off these two products. Now, you can see that it is true you are provided with a chemical reaction, but in this case, you are not so sure whether this reaction is endothermic reaction or it is exothermic reaction from what you have just studied. You are not given delta H on the product side. You are not given delta H on the reactant side. Again, you are not told that the overall reaction has delta H that is greater than 0 or less than 0. If one of those were provided, we are going to be able to conclude whether this reaction it is exothermic or it is endothermic. Now, let us continue to read further. Now, the potential energy graph below shows the change in potential energy for this reaction. It is true, this reaction to take place, the energy it is involved throughout the entire reaction. The energy needed for reaction to take place, the energy needed for the energy that is going to be released during this game, there are many energies actually involved. But now let us try to go through this potential energy graph. Now, potential energy graph is a type of a graph that will also help us to determine all of the energies that the reaction will be experiencing. Again, potential energy graph will help us to determine whether this reaction it is endothermic or exothermic. In this case, like I said, we are not given delta H in this reaction, whether it is on the product or reactant or delta H is greater or less than 0. We are not given, meaning this graph will help us by the end of the day to determine whether this reaction it is exo or endothermic reaction. Now, this graph on the y-axis, we have the potential energy, and then on the x-axis, you have the cause of reaction. Be careful. Know how to redraw this graph, okay? Know how to redraw this graph based on the given information. All the times on your x-axis will be your cause of reaction. On your y-axis will be your potential energy. Now, 7.1, it reads, or in fact, you know what, before we can even analyze this, we can just, answer whatever that we know based on this before we go through the questions. This is what I love to do, okay? Before we can even go there, let me show you something. So your potential energy graph, it can be like this. Or your potential energy graph, it can be like this. Okay, so now, like I said, these potential energy graphs, they're gonna help us to determine whether the reaction it is endo or it is exothermic. You can see that the ending point of these two graphs are not the same. The ending point here, it is low. The ending point there, it is higher than this one. You see, we have this starting point and then we end over there. It is high, the ending point. Here we have this starting point and then the ending point is a little bit lower than the starting point. That's the difference. Now, between these two potential energy graphs, which one is exothermic, which one it is endothermic? This is what I love to do. I love to simplify things, right? So that we do not forget or we do not confuse these two. So this graph, it is called it's for exothermic reaction. And in this graph, it is for endothermic reaction. But you want to ask me this simple question. How do I know that, or how was I able to see that this is exo and this is endo? Let me give you a tip. Exo is for exit, okay? It's for exit. You need only this one. Automatically, you know that one. Exo is for exit. So I love saying when my thing starts at the top and it goes at the bottom, it exits at the bottom. Everything exits at the bottom, okay? So when you see your graph exiting at the bottom, exit at the bottom, it is exo. Exit for exothermic reaction. That means if my graph, it is not exiting at the bottom, that means it is endo. I don't even have to complicate things. If it is not exiting at the bottom, it is endo. But I know exit at the bottom, it's exothermic reaction all the times. So now this reaction, we are not provided whether it is exo or endo. Like I said, we're going to use this graph to determine whether this is exo or endo. So look, we have the starting point and then it exit at the bottom. Exit for exothermic. So that means this potential energy is for exothermic reaction. If you want to answer 7.1, is the reaction endothermic or exothermic? Give a reason for your answer. What are you going to say? This is simple. It is exothermic. Can you see that? So that means here we have the exothermic reaction. Now, what's the reason? What's the reason? Why do we say this not energy? Why do we say that this reaction, it is actually an exothermic reaction? Now, this is very simple, okay? Like I said, you need to know your reasons. So here, the thing is the reactants are at higher energy and then the products are at lower energy. Okay, so that means here delta H is less than 0. So to answer this question, we say our answer here is going to be exothermic. Exit. Why do we say this is exothermic reaction? It's simply because reactants has higher energy than the product. Okay, this is your reason. Let me show you why does this actually make sense. Now look here, né? Let's say for an example, B, it is above C. Let's say for an example, because B is above, it's supposed to be greater than C, right? So let's say B is 5. I'm just making an example. Let's say B is 5. And therefore, we are C supposed to be less than 5. Let's say it is 2. So now when you want to determine delta H, this over here, it is enthalpy, okay? It is called delta H from here to here, energy of the reactants. To determine energy of the reaction, you're gonna say enthalpy, or you're gonna say H of the reactants, of the product. So of the product, subtract H of the reactants. So now what is H of the product? I said H of the product, it is 2, subtract H of the reactants, which is this part, it's gonna be positive 5. So 2 minus 5, we're gonna get negative 3. The answer, it is negative, meaning our delta H is a negative number. For a fact that we get negative number, that simply means the reactants has higher energy than the products. So when the reactants has higher energy than the products, what are we going to say? We're going to say the reaction, it is exothermic. And then, again, what I have just explained on the previous question, when your delta H, it is a negative number, you know that it is delta H. So some learners, they tend to forget that exothermic, it exits at the bottom. This is what I always say to them, okay? I always say, give yourself some numbers, okay? Let's say, for an example, here you choose to be 2. So that means this thing, it's high, right? It's supposed to be greater than 2. Give yourself, maybe it is 5. Same applies to here. Give yourself that it is 2. This is below 2. Maybe we can say it is 1. So when you want to determine delta H of this reaction, what are you going to do? You're going to say the product minus the reactants. The product, it is 5. The reactants, it is 2. So 5 minus 2, it is positive 3. And then here, you're going to say delta H, it is the what? It is the product minus the reactants. Energy of the products minus energy of the reactants. The product in this case, we assume to be 1. Supposed to be less than 2. We assume to be 1. And then the reactants is going to be 2 minus 2. So 1 minus 2 is how much? It's negative 1. So here we get negative number. And then there we get positive number. When delta H is positive, we know we're talking about endothermic reaction. So when delta H, it is negative, we know we are talking about the exothermic reaction. So if you forget that when it exits, you can just do these further calculations. Just give yourself a number just to remember whether it's exo or endo. Therefore, you'll be able to figure it all out. This graph is actually for exothermic reaction. So given the reason for this, the reactants has higher energy than the products. Now, 7.2, it says to us, use energy values A, B, and C indicated on the graph and write down an expression for each of the following. So now, they want us to write down the energy of the activated complex, okay? So now, activated complex, it is this point over here. We call it an activated complex, okay? So the energy of the activated complex for 1 mark, we're gonna say it's letter A, yeah? And therefore, the activation energy of the forward reaction, the activation energy of the forward reaction is from A to B. So why is this activation energy of the forward reaction from A to B? Simply because for this reaction to take place, we need an activation energy. Remember that. So that means we need this energy to reach the activated complex. We want to break the molecules between barium hydroxide and nitric acid. When we break the atoms between these, we're going to need this energy from the reactant side, from there to there. So this is what we call the activation energy, meaning this interval over there, which is A to B, we call that activation energy of the forward reaction. And therefore 7.2.3, it says delta H for the reverse reaction. Now remember, I said to you, some reactions, they can indicate to you they are reversible or they are what? They are forward or reverse reaction. So delta H for the reverse reaction is going to be B to C, okay? It's going to be B to C. So now, remember, they want delta H for the delta H, it's enthalpy. It is the total energy of the reaction. So that means for the forward or for the reverse, enthalpy will be the same. So we know that the energy of the products minus energy of the reactants, we get this thing, which is what I have just showed you over there. That's why I was using these figures over there between the reactants and the products. So the energy that we get, which is this interval 116 kilojoule per mole, it is the value between the reactants and the value between the products. So this interval, it indicates what? It indicates the energy of the either forward reaction or the reverse reaction. Because this, it is a reverse reaction, this, it is the forward reaction. If this is the reverse reaction, we'll take this to be our reactants and that to be our product. Still, if you want delta H, you're going to say product minus the reactants. You're going to get the very same interval. Now, 7.3, it says to us, calculate the amount of energy released during the reaction if 0.18 moles of barium hydroxide reacts completely with the acid. Now, this is what I like to say. According to this balanced chemical equation, we can see that 1 mole of BaOH2 can release what? Can release energy that is equals to, according to this, 116, because this reaction, it accounts for this graph over here. It can release energy of 116 kilojoule per mole. So that means if 1 mole can release this, that means 0.18 mole of the very same barium hydroxide can release energy of how much? We're going to say this 116 multiplied by what? By 0.18 mole. So when you purchase on a calculator, this will be the energy that can be released by 0.18 mole of barium hydroxide, which is on my calculator 116 multiplied